in section 2.4, we're going to be looking at derivatives of trig functions now. And we're not going to develop it pretty much based on the limit definition. We're going to be able to utilize some of our shortcuts we learned in 2.3. But I would like to integrate a little bit of trig into finding limits, just so that you guys have some experience should this come back again. So I'm going to try this out at first with just trying to understand some useful limits that happen, because a lot of times we see these in some of our expressions. So the first one I'm going to deal with is the limit as x approaches 0 of sine of x over x. And I'm telling you it's equal 1. It's okay for you to use this, but let's try to understand why. And remember, if we were to try to deal with this, we have issues with the x approaching 0. If you notice, if x is in the denominator, it makes the function undefined. So what I want to look at is the graph, and you could use your TI to help you explore this. I found a prettier graph on Desmos, so I decided to graph that. So I'll reshare that screen with you. There we go. We see our Desmos graph. It's got sine in it, so there's a bit of a wave behavior. The only thing that we're not seeing when we explore this is that the function is undefined at 1. So if we were trying to trace along these values, we would try to see that we don't have a y value for x equals 1. Excuse me, x equals 0. So let me go back. We'll draw a quick sketch just so that we can get an idea. And again, feel free to integrate your TI to help you understand why it's undefined. So we have some sort of wave going on. But if you look at the x values, as they approach 0 from the left, you'll notice that the y values seem to be approaching 1. And similarly, as you're looking at the x values, as they approach 0 from the right, the y values also approach that same value, 1. So in other words, we're just going to say the limit is equal to 1. Now you can do this as well if you want to look at the opposite. What happens if x is in the numerator, sine of x is in the denominator? Again, if we were to try to plug in x equals 0 at first, we would find out sine of 0 is still 0. So we have some issues there. So you could then also inspect this. I just decided to use Desmos. It was a little faster for me to not have to worry about the zooming in. But I'll reshare that with you. I created another graph, and it kind of looks like a parabola. You can kind of zoom in on it if you see, or zoom out on it. But if you were to look at the value of x at 0, so x equals 0, if you go through your TI and you try to punch in values, you are going to have an undefined right at y equals 1. So x equals 0, y equals 1. So I could draw a quick little sketch for our notes. And just kind of keeping in mind. So we have ourselves something that kind of looks somewhat like a parabola. And again, as x approaches 0, you're always looking at what's happening. As the x values approach 0, the y values are approaching 1. And the same behavior on the other side. The y values are approaching 1 as x values are approaching 0. So we want to use these useful facts, and it's okay. As this geometric argument is going to be good enough for calculus 1 purposes. So as long as you kind of have that down, we'll work with it. But we're going to use these facts to help us find other limits involving some of the trig functions. So along this argument, the next few examples, just calculating a few limits, I want to find the limit as x approaches 0 of sine of 3x over 3x. And the issue is we want to be careful. This is not quite exactly like our original useful limit fact. I'm sure if you graph it, you can make the argument and figure out what it is. And you'll see it's kind of the same idea. But the way they try to describe it to help us a little bit with mathematics as opposed to geometric arguments, they kind of use a bit of substitution in a way. They want it to look like our useful limit up here. So they decide, they just choose a letter. Maybe we use R, doesn't matter. They let R approach 3x. So if that's the case, if R approaches 3x, then as x approaches 0, R will approach 3 times 0 or 0. So what they end up doing is they rewrite this limit the limit as x approaches 0 of sine of 3x over 3x. They kind of rewrite it so that we kind of have the same notation, but we have just kind of did a quick change of a variable so that we can apply our useful facts. And this is the fact. You have the sine of x over x, or sine of r over r. If r is approaching 0, then we end up getting a 1. So it's a little mathematical hand waving there. But from now on, you can use these facts as well. So there's no real proof needed. But I'm always looking for, if I have a limit as x is approaching 0, if I see a sine function involved, I want to see if I have a matching argument with something in the denominator, or if it's the other way around, we're looking at this matter. So let's be on the lookout for that. And surprise, surprise, example 2 has some sort of application of this. So I'll kind of keep that in our minds. But I would like to notice, or note for yourself, is that the argument at this point, caution, the argument of the sine does not match the denominator. I thought you were like, wait, I thought you told us that it's supposed to work out, and why can't we apply it now? Well, let's play a game. A lot of times this is what we do in math class. We play a game of, wouldn't it be nice if we had, let's look at our argument. It would be super nice if we had a 2x in our denominator. And a lot of times when mathematicians want something to happen, they make it happen, of course, with sound mathematical math. If I want a 2x in my denominator, and again, I am looking at my argument of the limit, why don't I just put it there? But if I do that, I have to make sure I multiply the numerator by 2x, so I'm not changing the expression. So we want to be careful with that. So then we play a little bit of a game of algebraic manipulation. And we try to see, as the limit as x approaches 0, I'm going to keep the sine of 2x involved. And I'm going to do a little bit of reversal. 3x times 2x is the same as 2x times 3x. So I'm going to rewrite it so we have the sine of 2x over 2x. And I'm going to keep the 2x in the numerator like we had, and then we're just rewriting so we see the 3x. So now what happens to those x's, take a little time here, I see that the x's divide out. And if the x's divide out, I'm going to rewrite this just a little bit so that we can really pause and think about it. I have sine of 2x over 2x and times 2/3. Well, now, my friends, we have a limit times a constant, or maybe if I want to be a little bit more precise, technically everything was in the argument at first. And so if we have the limit of a function times a constant, we are allowed to pull that constant out. So in our case, the constant was the 2/3. And then that's multiplied by the limit of sine of 2x over 2x as x approaches 0. And so now we know from our useful fact that this is 1. And we end up finding the result of our limit from example 2. So 2/3 times 1 is going to give us a 2/3. I'll write it off to the side so I don't run into my next example. So this concept of introducing something, quite useful here, and you'll see this trick a little bit later, but we'll keep that until then. So remember, we can only use the useful limit fact when we see the sign. There might be other calculations, but right now we're just going to go off of this definition or fact. So again, if I see something with a tangent in it, I'm suspicious, but I want to be able to introduce the fact that I already know. So there's something we already know about a little bit of trig. Instead of writing tangent, we know that tangent is equal to sine over cosine. So I can take this piece right here, tangent of 3x, and let's rewrite it as sine over cosine. Maybe I'll do this in a different color, slightly different color. Excuse me, sine of 3x here we go. So sine of 3x over cosine of 3x, being clear about who's the argument. Now remember, this was still all over 7x. So we have a complex fraction, and a little bit of math will allow us to manipulate this so that we no longer have a complex fraction. So what I'm looking for at this stage, I'm going to see the sine of 3x over the cosine of 3x, or 7x cosine of 3x. A little bit more useful way to approach this. And so now we're kind of looking at this in this manner. I'm going to play a game again. Not the game of crossing the sign out. We're going to play a game of highlighting it so I can really adjust this. The game is, wouldn't it be nice if we had a 3x in the denominator? And yes, it would be nice. So this is where I do the introducing. I want the 3x in the denominator, but if I introduce it to the denominator, I have to introduce it to the numerator, a little property of fractions. So now what happens is I take a little time, even though a lot of things you can look at mentally. Sometimes if you go back to your notes later on, I'm going to play the game of rearranging things so that they are nicely put so that I can apply my properties. So I still have the sine of 3x in the numerator. I'm going to take the 3x I introduced from the denominator. The other thing I'd like to rewrite, there was a 3x in the numerator that I introduced. And in the denominator, we had a 7x cosine of 3x. So now I can play around and say, well, I know the x's divide out. And I also know I can play around with some of the properties, but I know the limit right here, the limit of this statement, if this will let me write, there we go. That's going to give us a 1. And if we do some direct substitution at this point, we should have 3 over 7. And you're kind of wondering, well, I thought we have an issue if we plug in x is 0 in the denominator, but we have to remember the property of cosine. When we're dealing with cosine, the cosine of 0 is actually 1. So if we want to play around with this, we end up having 3 over 7 times 1, which is 3/7. So a little bit of algebraic manipulation. If you want to even inspect this on your TI, sometimes that's even helpful. If I want to maybe type this in, might be a good thing. Sometimes you guys don't believe me, so let's see. I'll share, open up that TI for us. You can play with Desmos too, that might be faster than loading this program, but yeah, I'm already committed. So let me share this with you. There you see me, I was trying to play around with the window for zooming and I didn't have the patience. But I'll plug in tangent of 3x. And maybe because I'm paranoid, different calculators have different issues. I want to be clear that I am making sure that all of tangent of 3x is in the numerator and it's divided by a 7x, according to our original graph. Let me zoom it to standard for now, and then we'll go from there. Oh, pretty. And so we want to look at a little bit closer. I don't know if it's even going closer. We can zoom in. I want to kind of see around 0 what's going on. Zoom in a little closer. I keep zooming out. Maybe I should just leave this to you guys. We're so close. We're so close. So we're getting something that may work out. I'll have you play with it. Let me make sure I type this in right. Tangent of 3x divided by, oh, here's what I do. Let's see. Aha. One of the benefits of not having anyone around is I get to talk to myself. And then I don't catch that I did not enclose the entire denominator. Let's try this one out again. That'll be better. Now I'm zoomed way too far away. Let's zoom back. Let's zoom out. I want to zoom out one more time, just so that we can see. If we were to press trace, and we just have to figure out where we're located. Aha, there we go. We're trying to figure out what's happening around x equals 0. We notice it's undefined because this is the reason why we had to play with this. But you might want to look at the corresponding y values, kind of right by them, and then see how close they are to 3/7, which that's what the limit should be approaching. So hope that helps out. Again, don't make the same mistake I did. Make sure that whenever you have more complicated terms or products in the numerator or denominator, make sure that each numerator and denominator is completely enclosed in parentheses. That could throw the graph off like we saw. So that kind of helps a little bit with some limit calculations when some of the trig functions are involved. We're finally going to get into trying to understand, how are we understanding why, when we take a derivative of a trig function, why does it end up being another trig function that you get? And you can play around with limit definitions, but that's kind of beyond the scope of what our class is. I'm actually going to go back. I'm going to go back and revisit, I believe, section 2.2, just a little bit, and kind of bring you back to recalling when we knew what the original function was, and certain points along the function gives us hints about what the derivative is going to be. I want to pull that into this section to provide some justification. That way you kind of understand, why is the derivative of sine cosine? That's the big culmination at the end, but let's talk about why. So this is the graph of sine of x, even if we didn't know, we can now see what we can do. Try to sketch the graph of its corresponding derivative. So again, what I like to do is see if I can identify where I see horizontal tangent lines. That's kind of the first case. That was a little trick we were using in 2.2. So among this, it kind of, I am seeing we have a horizontal tangent line about here. I'm seeing here, and it's a periodic function, so we're going to see a lot of horizontal tangent lines. So this is where you'll see me kind of mapping. This kind of breaks up the x-axis a bit for me, so I kind of map everything down, break up my regions a bit. I know this is not part of the graph. There's not really an asymptote, but it's just a useful way so I can visualize the separation of my regions. Doing my best. Maybe I should have made a smaller version, but it's okay. I'll just take the time, separate my regions out. Now remember, when your function has horizontal tangent lines, that means the slope or the derivative is equal to 0. So when we mark what our derivative graph is, if this is the graph of f, this is the graph of the derivative, that means that everywhere we saw a horizontal tangent line, we should be intersecting the x-axis. So I have a few of those. So I mark where those are. Now the next thing I want to do is I want to look at the behavior of f. Maybe I'll write it off to the side. We're going to look at the behavior of f between those zeros. Of f prime. In other words, let's talk about what the function is doing. What are the slopes looking like when we're looking at this region? So it looks like the function itself is increasing. And if we move on over to the region from here to here, I wanted to highlight that. See that? What's happening in this region? We are decreasing. And similarly, a little bit more ideas here. Remember, if I'm talking about increasing, for every x value that gets larger, the corresponding y values are getting larger. You could also kind of talk about the slopes of the tangent lines. So if you draw a bunch of points and try to draw in what the tangent line would be in any case, you see that you have slopes of positive lines. Or I should say lines with positive slopes. There we go. So similarly, I'm kind of looking at the regions, and it helps for me to understand, okay, I know I'm decreasing. It looks like I have, if I draw little points and tangent lines, no matter where I draw them, the slopes are negative and they look like they're indicating the function's decreasing. And we have this increasing business going on. So now we use this to justify what's actually happening with our graph itself. If we know that the function's increasing, we know that the derivative for all the increasing pieces, and I'll try to highlight them so that we can see, all those x values should give us our derivative to be greater than 0. In other words, it should be above the x-axis. And all of those portions where the original function is decreasing, it should give us our function below the x-axis. Negative y values versus positive y values. So when we kind of play with this, we kind of see that we are getting about the same idea, and maybe I can even be a little bit more specific. I want to see how far do I go, up or down. Yeah, let's look at this. Let's look at where we hit our actual values. Let's look at where, some critical points along the way. And I'm using a lot of color here, so I'll try my best. Some nice, pretty points. What is happening at maybe 0 and pi? That's kind of useful. And maybe negative pi. In all those cases, if you were to take a snapshot of the slopes at all those times, it looks like we keep getting well, I don't want to draw all of them together. Give me a second. Just take a snapshot of this line. It appears that this slope is -1 around here. Negative slope, right? This slope. It's hard for me to label. I don't want to get you guys too confused, but maybe it's too late. We'll see. Sometimes I have to watch the video a couple of times. So we have negative slopes if we're kind of looking at what's happening along this point. And maybe at x equals 0, I have the slope to be +1. So that could give me some justification as to why at certain values I have a bound. So I have -1 slope, or the derivative is -1 at this point. And then at x equals 0, the derivative is +1. This could give me some justification of why I'm stopping at certain y values. And then now go through and we can say, well, if I'm increasing, I need to be above the y-axis on all those yellow regions. And it looks like the way the graph is appearing, we're doing something like this. If I'm increasing again, I have to be above. And if I'm decreasing, I have to be below the x-axis. And we finally get a pretty darn good representation, asking ourselves, what does this graph look like? And I already gave you the hint at the beginning. But doesn't this look like very close, or looks like the graph of y equals cosine x? And if you're saying, I don't know, you tell me, well, I'll tell you, yes, it's like the graph of y, it is actually the graph of y equals cosine x. It's not a proof, but it's a pretty good, reasonable argument as to why, this is what we're trying to develop, the derivative of the sine function with respect to x, or sine of x, actually equals cosine x. So we could justify this analytically using analytic geometry to justify why the derivative of sine is cosine. And it's okay if you already knew that, but maybe you're looking at it a different way. I got one more for you. This kind of interpreting the graph of the derivative based on the graph of the original function, it is quite complicated. It's not always a straightforward procedure. So I'm going to demonstrate one more time, and then we'll get into what a lot of people like. You like the computations a little bit more, but bear with me a little bit more. Still trying to develop that part of your brain. So let's do this again. And you'll probably see, okay, well, this looks very close. This f. Most likely, this is the graph of cosine. So, yeah, we're kind of even looking up here. Yeah, we can even use our TI. But I want to do the same process. I want to analyze. I want to mark where do we see horizontal tangent lines. So this would be able for us to mark where our derivative would be 0. So I kind of can tell, okay, anytime I have a max or a min, I've got these horizontal tangent lines. So that's helping me break up the region, the x-axis, into a few different pieces. I like to, just because I don't always have all the highlighters, I always like to kind of go straight down to the graph. And I know that the derivative, the graph of the derivative should be 0 at the horizontal part. Do the same thing. So I'm marking on the x-axis. What's going on? Some of you are just probably fast forwarding at this point because you kind of already know what's going to happen. But remember, you might have to do this on a test, so it might be a good way to rewind. You won't hear that if you fast forwarded, though. Oh well, we'll go with it. Here we go. So this is a little tedious, I get it. But I always like to line the graphs up right under each other. It's a really good technique to help you see where you have the derivatives equal to 0. The other case now, you can now separate your regions up a bit. You can say, okay, well, it appears for each of these regions that I'm seeing, I appear to have a decreasing function or decreasing f. Looks like this region and maybe this region right here, for sure. And you could do that by inspecting slopes of tangents along all the different points along the way. If this helps you draw mini tangent lines, this is going to help you. So we know we have decreasing function. So what that tells us about the f prime or our derivative, that we should have the f prime to be below the x-axis for decreasing functions. And so sometimes if you want the words, the English for below, sometimes that's helpful. So below x-axis. And then look at your other regions. It appears kind of similar to our last example that we have some increasing regions. So that gives us a case of if we have increasing, we should have our derivative be positive. And that would be above the x-axis if you were trying to explain it. So if you would like, if it helps you highlight the regions, go for it. It's not always necessary, but I can kind of remember, okay, I know that these I should have above and corresponding. Now the other thing is I noticed this original function's bounded. So what I like to do is I kind of look at some of those critical points, generally where you see your 0, pi, 2 pi, etc. I'm really concerned, the function itself, it looks linear if I only take a snapshot around some of these critical values. And it actually happens to be, if we do the calculation, our slope along these critical values, I just have to be careful how I label them, but it looks like I have a negative slope, and it is about 1. And for the yellow, the yellow regions, the slopes would be positive 1. You have increasing function, positive derivative. So it really helps. You can kind of then say, well, if I'm trying to correspond this to the graph of my derivative, I have an x value that should have this, where the derivative is -1. So I have derivative -1 in the regions where they're trying to tell you the derivative is below the x-axis or the graph. And then I have a +1 in the regions where the derivative is positive. And that has to do with the slope of the tangent lines at that point. If you zoom in really close, it does look like a line. So now we do the same game. We now can draw our graph based on what we think is supposed to happen. And remember, if we're kind of writing notes to ourselves along the way, we have something that's below, something that's above, something that's below, and something that's above. And so a lot of you may have jumped through this and you're like, oh, I know, I have sine. And yeah, I mean, it almost looks like sine, but it's not quite sine. So remember, sine of x, you guys recall, we just graphed it. Well, y equals sine of x. We start at 0 and we go from there. So if we played with this, this appears to be the sine graph, but it would be the sine graph if it was reflected about the x-axis. So actually, this graph right here that we graphed is y equals, whenever you reflect something about the x-axis, you were wondering when chapter 1 would come back to haunt you. You have a negative sign outside the function. So here we go. We actually have a conclusion. If you want to take the derivative of cosine x, that actually is negative sine of x. So helping you develop this, I wanted to kind of use the geometric argument to maybe refine a little bit of 2.2 with you. These two facts, by the way, you do get for free. You don't have to prove them every single time. But if we run into the other trig functions and they specify they want you to prove them, you're going to be utilizing these two facts in some way or another. And some we're going to incorporate the computations from 2.3. Everything's building on itself, so we want to be careful here. So, having said that, eventually you're going to get excited because you get to memorize these things and you don't have to prove them. But keep in mind, example 6 is specifically asking you to prove that this is happening. And the good news, maybe for some of you, is that you don't have to do this graphically or geometrically. Let's utilize what we are pulling from the other sections. So I want to make sure, I got to do a little bit of trig review, but I need to prove that the derivative of the tangent of x is secant square x. So again, if this is a proof, we always want to start off by what is either on the left side or the right side. It appears that the left side, to me, it's more complicated. It's kind of like an identity because it involves taking a derivative. So I'm going to start off with the left side. And then I'm going to try to see, is there any way I can rewrite tangent in terms of sine and cosine, because I have a little bit of knowledge about their derivatives from our previous two examples. Pause for a second, let you think. And we can say, I didn't calculate the derivative yet, but derivative of tangent would be the same thing. Trig identity coming back our way. Sine x over cosine x. And now we have two facts. This is a quotient of the two functions. We have to be careful though, was when we have the quotient of two functions, we don't just take the derivative of the numerator, derivative of the denominator. That's not how it works. We can use the limit definition to prove why that doesn't work. But we have to go back and use the quotient rule. So that's going to be key here. And the quotient rule tells us that if you want to take, I'll write it off to the right side, the derivative of a quotient, recall, bring it back. That is the second function multiplied by the derivative of the first minus the first function multiplied by the derivative of the second, all over the second function squared. Gf prime minus fg prime over g squared. Or sometimes people say, what is it? Sometimes people call the f part, I'm trying to remember where it was. This is the high, because it's on the function on top. This is the low function on the bottom. So play along with me. Low derivative of high, low d high minus high d low over low low. There's better ways to do that. I think there's some songs too, but I'll leave that up to you guys. So main thing is we have the formula correct. And when we're trying to calculate the derivative, we're going to want to go through and label who's our f and who's our g. Just remember, the top function is always f. So in our case, our f is sine x. The denominator function is g. So in our case, it's cosine x. And then we're going to allow ourselves to calculate the derivatives. So we have f prime. The derivative of sine, where we just learned, is cosine x. And the derivative of cosine is negative sine x. Be really careful. So we're going to plug this into our formula. Going to take a little bit of space. We're looking at the second function. So we have ourselves cosine of x times the derivative of the first function. That happens to be a cosine x as well. There's a minus sign from our formula. We have our first function, f, that's sine of x, times the derivative of our second function, that is negative sine of x, all over the second function squared. So the second function again was cosine. And if we were squaring it, we could actually use the notation. It's a little better if we see it this way. Some of you might recognize it from trig class. If you want to speak about squares of trig functions, you'll probably see the notation where the exponent is in between kind of the argument and the name of the trig function. They both are correct, but be careful. So if we want to say cosine x times cosine x, on the top, that's also cosine square x. Now sine x times sine x is sine square x. But then we have negative times negative, or minus a negative is going to give us a positive. And what we have right here, we have ourselves a Pythagorean identity. Sine square x plus cosine square x equals 1. Remember, our job is to get it to look like secant square x. So we are almost there. So the final part would just be using the trig identity to remind you that 1 over cosine square x is secant square x. We have just shown that the left side of our statement, derivative of tangent x, equals secant square x. And then we have properties summarized for you. You could be asked to derive these as well. Maybe if I ask for secant, cotangent, cosecant. So try a few of these so that you're comfortable. And it's really pulling in not just your algebra, but your trig identities from your past and how you manipulate those. So you're wondering, why did you have to do that all in trig? It comes back to haunt. Or maybe I should say surprise. So play around with them. You won't have to prove them like this all the time, but it's a really good application of why we would use a quotient rule. Last example. This would be kind of something that we're looking at, maybe computations, just kind of how do we utilize once we understand these facts. So just one more kind of application of understanding well. If I'm asked to take a derivative and it's a complicated expression, it's not just a nice little x square or anything like that, I want to pay attention to what's going on. And it appears that if I'm looking at finding the derivative of 3x squared sine x, even though you don't see it, sometimes it's really helpful to remind yourself that you've actually got a product of two functions. So that's where we have to use the product rule. And then if you remember the product rule, you can write it out for yourself just to kind of help you go through this. The product of two functions, or the derivative of the product, we would say gf prime plus fg prime. There's a plus there, not a minus. Kind of dealing with that ahead. Okay, here we go. It's very useful to know who your first function is and who your second function is. And it would also be nice, maybe kind of off to the side, we'll organize scratch work so we don't mess up. We have f, we have g, and calculate their corresponding derivatives. So f prime, that's one of those power functions. We should have derivative is 2 times 3, 6x. And the derivative of sine x is going to be cosine x. So having those first intermediate calculations will help us out with our particular answer. So the derivative of your function, we're going to utilize this product rule. Our g, that's our second function, that's sine x, is going to get multiplied by the derivative of the first. So that's f prime, which is in our case 6x. We have added to first function, which is 3x squared, times the derivative of the second function, which is in our case cosine x. So we're utilizing the product rule, and this is actually where the product rule is more useful because we wouldn't know. Not like those polynomials we were working on earlier. So we clean this up a little bit, and by clean up I mean sometimes we don't like to see so many parentheses. A lot of times you end up writing it's not really linear, but linear factor first in front of your trig factor. And that's good enough. At this stage, we don't have to really worry about it, but some of you may be looking at, oh, I see some common factors, and you're all in the swing of trying to factor out common factors. At this point, you don't have to unless the directions are specifically asking you to. I would leave it like this. The only time I ever play with factors is if I have to use this derivative to calculate something else. And that might be coming up in a little bit. So practice, practice, practice. You don't get good at this unless you keep working on your homework. Sometimes watching is fine, but you have to kind of struggle through some of the mistakes you make on these. And don't forget to memorize the derivatives of your trig functions. I will see you in the next section.